does anybody know why they're used or why they were born? Actually, the story is interesting because that gives you a lot of insight as to, so I'll keep it very brief. But the idea was when you normally have, everybody knew how to solve a set of linear equations, right? So if I give you and so on, and if I give you a system like this where and so on, then everybody knows how to solve it. We can frame it as a linear system, we can solve it, and all this is fine. But in many applications, this was not the form things were, right? For example, if you have, instead of a linear system, so Gauss, the name from which Gaussian comes from, he was studying heat. And if you're a mechanical engineer, then you know that when you study heat, you have some partial differential equation. So he had some partial differential equation. So instead of this, you may have, so you may have this form. So this is a partial derivative of that function with respect to x. Now, they had a system like this, right? And the heat equation, this is not exactly the heat equation, but I'm just giving a general. Now, they wanted to solve this system. And to solve the heat equation, they needed some framework to do this. And this turned out to be really complicated because most solutions for PDEs are like sort of a case-by-case basis. You need to take the PDEs and know what the function is, actually do the derivative, and so on. But Gauss had this brainwave, right? So what he said was, if I could somehow transform this into a set of linear equations, then I'm going to have a lot of power. I can use any linear solver, solve it, and then necessarily I need an inverse. Right? So if I can somehow, now if you think like how we solved today the integration problem by splitting, if you think through this today, you will come up with the Fourier transform, right? It's actually not that difficult. What the main idea was identifying that you need to go from here to this space. It was not in identifying what this transform is, right? And once he identified what the transform should be, it took another 40 years for them to prove whatever we know about Fourier transforms. But Gauss had laid this down way before Fourier and all these guys, right? And Fourier and all these guys were his students, who suddenly realized, oh, we need to prove this, otherwise it's not usable here. We need to prove this because it's not usable here, and so on. But Gauss had identified this several years before that. Okay, so now if you think about how do I transform this set into this set, what do you need? The core element is each of these need to go to each of these, right? Somehow. So somehow we need some operator that takes this. So we need an operator here which takes dou f by dou y or dx by df by dy and gives you something that is just a scaled version, right? So some lambda times something like that. We want this differential operator to become a scaling function. Right? We want a differential. So right now, this is f. We have applied a differential operator to f. Now, if that operator just gives me f but scaled by some lambda, then what happens is, this would be beautiful. I can simply go there and every one of these will get replaced by f. And you will get this form. It may not be y, but you will get this form of a linear equation. Now, what does this mean? This is very familiar for people who studied maths, right? So this means that this operator here has the differential operator as its eigenfunction. So all these things in maths, actually, which I thought were highly irrelevant to us, became very, very relevant, right? I remember in school people teaching me eigenfunction of a matrix. I remember them teaching me partial derivatives. I remember teaching Fourier transform. Nobody points out these things, but they're very interesting, because what this means is, if you can find an operator whose eigenfunction is the differential operator, then you have solved all of this. You convert, and that is how the Fourier transform was born. Because if you take e to the power lambda x and derive it, you simply get. So Gauss realized that whatever I need to do needs to use this, right? And I remember the first time I saw complex numbers, I was like, somebody must have really been mental to discover this, because nobody understands why it is relevant, right? But if you look at this, it's really beautiful. You can work everything back. Then once you have this form, you go back in there, and then you will see why also you need. So there's, of course, the Laplace transform, which is what lambda is. And in the Fourier transform case, it's a complex number. But those are details, right? And people needed many constructions to prove. So if you look at the formal statement of the Fourier transform, people will say things like, oh, it needs to be a square integrable function, and on. And the mathematicians have a lot of constraints. The reason those were born was out of these. So Gauss simply started with this high-level idea. He said, oh, this is beautiful. I need some operator which does this. And he was like, oh, wait a minute, this is very easy. I know this. And then he did this. And then he went back and he said, my operator is an exponential. And then he put an exponential there. He took everything back and everything worked. For his particular case of the heat equation, this worked. And that's why we attribute that result to him. And then his students went and they said, wait a minute, but if you want to do this more generally, the function needs to satisfy A, B, C, all these properties. And then they tuned this thing till it became the Fourier transform that we know. Right? And I'm not even going to write it's in the notes that I'll distribute, but I'm not going to write the definition of the Fourier transform, because once you know how it's born, you can derive this anytime. Right? You don't even need to know the derivation. So that's the beauty of the whole Fourier transform thing. Okay, now why is all of this relevant? So the reason it's relevant is this thing we've been talking about in terms of priors, right? So what this has done is it is telling us that this set of linear systems we will get at the end is going to be in terms of exponentials. So somehow, whatever function we get, we are going to represent it using exponentials as the basis. And I'm hoping all of you know what a basis is. So you have these as the basis functions, the exponentials, and you're going to set up your whole Fourier transform so that you have complex exponentials. So instead of lambda, you will have 2 pi I, which is a complex, whatever lambda is. And what that means is, because of Euler's formula, you can say right? This is Euler's formula, which said you can take any complex exponential, and you can see how all of these now come in, right? And write it as a complex number, where you have 2. Now, the nice thing about this is it means whatever function we start with, we can in the end represent it only using exponential bases, which now means they become either sinusoids or cosinusoids. So we can start with all these complex functions here and go to represent them in terms of sum of cosine functions and sine functions. And that's our basis. Now, what this also means is if you study how to use a particular cosine, just any arbitrary cosine, you can apply this to any function, right? Well, not quite, because to be able to go from here to here, there are some conditions. Right? And one of the things that, so people will teach you discrete space. So they will teach you Fourier series. Some people will teach you Fourier transforms where the space is continuous, your function is continuous. But just realize that they're all essentially the same idea. Because of these conditions and the way you need to formalize them, you may write them slightly differently. In this case, we have taken a function and represented it as a Fourier series, here in this case cosines and sinusoids. So now any transformation I need to do to this function, I can apply it to this. And if it's a linear transformation, I can open it into the sum and I can apply it to each of the cosinusoids or sinusoids and so on. This was very powerful because now I have some way to represent any function. And this is what we're missing in stratification. We don't have a way to represent any partition. We don't have a general basis or a set of strata which we can use. Perhaps we could use, so the mathematicians use these box sums. So you generate, if you have a regular grid, if you have any graph paper with the checks, you can take any shape and then go just to the nearest box or something like that. Right? That may be one way to partition, but it's not easy in high dimensions. It's not clean. Anyway, so that's very, very quickly, in 7 minutes, what happened over many, many years of the Fourier transform. And then there are several interesting properties that if you go home today and read properties of, hopefully if you go to Wikipedia and read Fourier transforms, first of all, you'll notice that a lot of what I said may even be there. And secondly, you may see why all these conditions make sense. And then we will slowly see why it is relevant to sampling. Right? Now, obviously, these conditions are important, and we'll also talk about them. I mean, the problem is we can just keep on going through about Fourier transforms, but for now I'll stop here. Now, just one thing today in the test, the assessment thing, the shapes I gave, is the reason is to see if you guys have already seen discrete continuous and you understand what they all mean. Right? So there were some of you who did, but many of you didn't understand why you can spot these things. So I would recommend that you read about Fourier transforms and discrete. Discrete Fourier transform. Right? Now, once they developed a fast algorithm to solve the Fourier transform and to compute it, suddenly we could solve PDEs really quickly. So the fast Fourier transform is a way to compute the Fourier transform on a discrete domain. And the complexity, computational complexity is quite good, which means that a lot of applications became practical. Things like solving the heat equation, doing stuff like that became trivial in terms of computation, right? And obviously they took many years for that to kind of get to that state. Anyway, so I would say if you read this today, you will definitely be able to answer the question that I asked, but I think it'll also set things up for further discussions. Okay. I hope this was new because, I mean, I think very few people teach it like this, but I really wish more people did. Somebody told me this once, and I was like, oh, why doesn't everyone teach it this way? Right? And I feel at least once you know this, you go and read all that stuff. It makes sense. Okay, so that's enough for now. Let's go to the lab. Does anyone prefer to work in groups, or do you all prefer to work alone? It's up to you. Does anyone have a preference to work in a group? No, okay. It's up to you. So when we go to the lab, what we will do is we will have, first of all, how many of you have worked on Linux? I know, very comfortable. Comfortable, yeah. You don't need any super skills, right? So there's 2 of you, and I think there are only 2 or 3 Linux machines. If you want to take them, go ahead. Otherwise, everyone can take a Windows machine. And what we will do here. So here's what I would like you to do. I would like you all, first of all, to generate random samples, right? And plot the histogram, convince yourself they are random and so on. Second, it would be maybe so the reason I'm giving you this is apparently it's going to take some effort just setting things up. Many of you don't have Octave. So just doing this means you would also automatically have to set up before you can do that. Okay. Second, I would like you to generate random samples distributed according to, let us say, f of x equals x squared, right? How about this? Because we don't have much time, let's just do these two. I suspect this should be very straightforward, right? It's just calling the rand function, but then you'll need to look up the call. So you can almost consider that to be just install stuff, so you can run. And this may be requiring a little more thinking. If you can't do it in the lab in the allocated time, that's fine. You can do it after class today, and maybe tomorrow we can continue from there. Any questions about what you need to do? Okay, so to do this, if you're going to Windows, there are two options. You can either use MATLAB, which means you have to get a demo, download a demo version. Is the internet reasonably good there? They should be able to download the installer. No, but the lab machines, are they on Wi-Fi or the network? So you can download there. So Wi-Fi may be hard, but if they're wired, you can download MATLAB license. If you want to do it on your laptops, that's fine, but then the download may take a bit longer. So they're not demo, it's called trial, sorry. So the trial version is valid for a month. You can download that if you want, or you can download Octave. And for the purpose of this course, both are equivalent. And I think they exist for both Linux and Windows, so you should be able to do that. So download one of these, install them on your machine. Do they have install privileges? I'll ask Bharat. I think you should have. And then, if not, you can install it locally to your user. And then it should be straightforward. Okay, any questions? Okay, cool. So I'll see you in the lab. And if you have any questions, you can ask me there. And for class, I guess we'll see you tomorrow. Do we start at 9 or 10 or 9:30? Can we continue 10? Okay. I am okay with anything. I don't want to. So one student asked me if we can start earlier. So, and that is okay with me because I'm on campus, but I don't want to commit for everyone else. So what yeah, I'm happy to do more if it's 9:30 to 12 also. Yeah. So even if you want me to start half an hour early and still end at 12, that's fine too. Or 12:15, that's fine too. The question is how many actually want that. So yeah, many people are, who's coming from, so I think one person's coming from far away, and despite that you wanted a early start. Okay. You can come in and do your labs in the morning. No, I think they may, if you ask them. I think this is all open all the time, right? Okay, so then I would recommend you use your laptop in your case, because you have a laptop. Then you can come in early, and I think you can, yeah. So I would say if that's the case, then maybe that's best. So okay, then we can keep it at 10. Then, right? 10 is okay. Can everybody get in by 10, or is there a problem? Okay, so then there's no problem. We keep it at 10. If after tomorrow, if you feel, so you guys can discuss, and I'm okay with 9:30. So if majority of you feel 9:30 is okay, let me know, and then we can do 9:30. Yeah, that's also fine. Yeah, or in the evening as well. I'm happy to spill over, and I think it can be more informal if the lab is not used immediately after your lab. I think it's okay, right, for them. Yeah. So the other thing we could do is we could do all of that in the lab after the lab. It'll be more flexible, right? So that way, if the space is booked anyway, that way people who are not interested to sit through it don't need to be part. Okay, that's perfect. So that's perfect. No, yeah, okay, but people probably don't want to stay that late. But what I'm saying is 3:30 is supposed to end. If you want to stay till 4, I will hang around. If you want to work after that, that's up to you. Okay, sounds good. Well, see you in the lab. I'll just remove all this stuff. Yeah, and where is the email list?